Okay, hello everyone. Well, today is our last class of this semester of the abstract algebra, okay? Can you hear me? Okay, so first of all, I have a question for you guys. Someone says that, well, your ODE course, your ODE final report is due on Friday night. So I also get an email say that we can postpone our final grade release Sunday.
Post-Tatinos has postponed the paper due to Sunday.
Oh, okay, that's fine. Then, well, yeah, since we can also postpone our grade release a little bit later. So, does anyone would like to postpone our final to Saturday, or we can keep it on tonight to tomorrow? Which one you prefer? Well, so who would like to postpone it to Saturday? You can raise your hand. So nobody would like to do that, right? Then let's keep it, and you will have your midterm today, okay? From 7 to 8 tomorrow, 8 p.m. tomorrow. Okay? That clear? So we will have our exam from 7 p.m. today to 8 p.m. tomorrow. Okay? And today, what we are going to do is we will do a quick review and basically finish the review, and maybe I'll try to tell you how to use a group series idea to play with the magic cube today. Okay? This is, I think it's a good application, and you can try to understand it by yourself. Well, I only have partial understanding of how to play it with group theory, okay? And then, well, I hope I can finish it at by 1 o'clock, and then until 3 o'clock, I'll be here and holding this office hour, because I heard that you have the final for the ODE course from 3 to 7, right? So I will hold it from 1 to 3 for the office hour, okay? And before we move on, any question? Any question? Any question about your final or something else? Any question? Okay, there seems to be someone who would like to postpone it to Saturday, okay? So let me ask you again. If you would like to postpone it, then you can click this, I think it's, let me stop sharing at this moment. I think if you would like to postpone it, please give me some reaction, like, let me see how to give reaction. Like on the reaction, there is a reaction button, and you can click it and use clap or thumbs up. Then I will know you would like to postpone it, okay?
Sorry, by postponing it to Saturday, do you mean by from Friday to Saturday?
From Friday night to Saturday night.
Oh, okay, thank you.
Okay, so if you would like to postpone it, please do something on reactions. Okay. Okay, I only see two, Hu Yue and Yi Shui. Anybody else? Okay, sorry about that. It seems not enough people who like to postpone it, so sorry about that. We will keep our originally time scale, well, as the schedule of the final, okay? So not a lot of people would like to postpone it. And well, yeah, anyway, it doesn't matter actually, well, but I think to do it earlier is not a bad thing anyway, if you do not have anything to do on Friday, okay? Any other question? Any other question? No? Okay, so let's do a review first, okay? Basically, what we learn in this semester. Well, this is so-called abstract algebra course, okay? So we have learned a lot of things about how to do this so-called algebra. You can see that all what we are doing are something, yes, something, well, when we try to learn something like the symbols, operations, we did that, right? I think since you are in the middle school, you try to do this kind of operation like x times y, x plus y squared, try to expand it, and a times b plus a times c is equals to a times b plus c. This kind of operation is so-called algebra operation, okay? And for this course, we try to find some structure about how you can do this kind of operation, which is why we call it abstract algebra. Okay, and in this semester, we didn't learn a lot. We basically learned three stuff. The first thing is some preliminary knowledge, which is so-called logic. Okay, and for the logic, well, it's not something very complicated. It's something you already know. Okay, but we choose it as a start of the semester, simply because, well, for this abstract algebra, it's nothing but try to explain something you already know by using some mathematical language, okay? So basically, this abstract algebra class is nothing but an, well, language class. It tells you nothing but language. Okay, whatever we use, whatever we try to do is something that may be in your mind for a long time, but you try to use some language to explain it to others. Okay, so which is why we try to start from logic. You try to learn some basic terms, some basic way to state a statement. This is a very basic building blocks of this language, okay? This is how to state a statement. A statement in a correct way. And among them, well, there are a lot of things we have learned, but among them, the most important thing is how to use the axiom, which is some assumption we assume at the very beginning to prove something. And you have to be careful that if you assume some assumption, then you can only use this assumption when you try to do the proof, not something else. Okay, this is very important when you try to, from the very beginning, to learn an area of math. Okay, and another very important thing, we use it again and again, is so-called equivalent relation. This is something maybe new for you. So this is something, well, you may use in order to prove something, right? We use the equivalent relation because it is important, because we can try to divide some set into equivalent classes by the equivalent relation, which is how we can deal with this group action. This is very important in terms of the group action, because we try to, well, divide a set, a group, into orbits. Okay, so this is something new. But beyond that, we also learn how to state a statement and how to use the axiom. How to use axioms. Okay, and this is basically what we've learned in logic. And then what we try to learn is the ring theory. Okay, well, the reason we try to introduce the ring theory is like we just start to tell you how to speak a language, how to speak some basic terms, some basic statements, some basic sentence. Then what we try to start here is we try to start something that has a lot of examples. And you have to be able to translate these examples that you have already known are translated to some modern math language, okay, using this language. So for the ring series, we basically introduce a lot of examples, okay, examples that builds you, well, an interpretation of, your common language you learn from your high school, from your middle school, to something in abstract algebra, okay? So for the ring theory, in some sense, the examples are the most important part. And of course, based on the examples, we review something. You've learned that a long, long time ago. And we also try to extend it a little bit, only a little bit, so that you can get something really new, okay? For instance, you have already learned what is long division, I believe, in high school. You have already learned how to find root of a polynomial, which I believe you already know. Well, at least some of you know how to find this root, okay, in high school. And we also learned something so-called the Euclidean algorithm. Well, which is something you may know if you learn the mathematical Olympics, but you may not know. You just know the existence before, okay? Or this kind of modular arithmetic, okay? Which is how you can do some algebra on ZP or ZM. This is something sounds really easy. It's just you try to check the remainder of this number and do some addition and multiplication. However, this kind of thing can be seen as the most important examples. Whenever you have some idea about some weird ring or weird group, then maybe you have to check those kind of ZP or ZM, okay? And well, then we also, after these examples of the ring theory, we also try to touch another part of the ring theory, which is more abstract, okay? And then because of based on this kind of examples, we are able to try to get some better idea about the abstract stuff. Well, and then this can be seen as a transition from concrete examples to some abstract theory, okay? For instance, we've learned what is homomorphism and what is a quotient ring. This is a very important concept in algebra, right? And well, if we want to learn what is quotient ring, we also need to know what is ideal. And also we've learned the big theory, which is a fundamental theorem of isomorphism. Fundamental theorem of isomorphism. So this part is examples. And this part is you use the example. You already know the example you are quite familiar with to some abstract structure. Okay, so these are the basic, basic thing we've learned in the ring theory. Then after that, we try to start the group theory. Okay, in the group theory, what you can find is compared with the ring theory, there are less familiar examples for you. Okay, so you can see that in the group theory, well, the examples we can see are always those kind of examples. Either it is a general linear groups like the matrices, or those kind of permutation groups like the permutations, or this symmetric groups of a geometric object. Those kind of things, those kind of examples, for you guys, it might be not that familiar with. Okay, it's not like the polynomial, not like the integers, not like those modulars, ZP, ZM. It's something more abstract. It's something you're not quite familiar with. Because on the group theory, we want to have the minimal assumption. And based on the minimal assumptions, you can try to use the abstract structure to say something that you don't really know. Okay, so this part can be seen as more abstract structures, and less concrete examples part. Okay, so for this part, for the group theory, I think, from my point of view, the key point or the key part of our group would be the structure of the group can be determined as we always see in Dn or something like Dn. It would be the order and the commutators. Okay, or the interchange rule. You can see that from the group, it is totally different from a ring. Because for a ring, we almost always assume everything is commutative. But for group, a abelian group and a non-abelian group are totally different. And the main problem we have when we study the group is non-abelian group. Okay, so for a group, the hardest part would be first, what would be the property of each single element? This is where we try to study the order of an element. Okay, another thing is we have to study what is the relation between elements, which is when you take A times B, how can you represent it in terms of A and B? Or when you have AB times A inverse, how can you write it in terms of A and B? Based on the order of a single element and the relation between two elements, you are able to determine the whole structure of a group, which is why I think these two are the key part. These two are the key part of a group. Okay, and you can see that is very different from what we have seen like, well, the integer, like the rational number, like the real number, like, well, ZP, ZM, okay? Not really the same thing. So this is something new. Which is why we can try to use some abstract concept in order to study this kind of group, okay? Then you can see the tool we built are somehow very powerful in terms of this kind of new stuff, okay? And for instance, based on this ring theory, we have, well, we also have the group theory, have the fundamental theorems of isomorphism. Okay, and we also have the quotient group instead of this quotient ring. And of course, when we try to introduce a quotient group, then we have to introduce so-called the coset and the normal set, the normal subset. Okay, a normal subgroup, I mean. And then after this, we have a better idea about groups. Then we find that, okay, for groups, we actually can do more. Based on this kind of tools, we are able to do something about counting, like the Lagrange theorems, the Lagrange counting formula, or this a group action, which is something still about counting formula, or class formula of a set or of a group. And well, we also, because we want to learn the structure of groups, we also have this so-called Seelos theorems, which seems to be very complicated theorems, but you can see that, well, the proof of the theorems seems to be very hard. But, well, the application of the theorems seems to be very, well, not that hard at least. It's something very useful. You can use it very easily, okay? Well, the most important application of Seelos theorems should be how to classify small groups. Okay, so how you can build a clear picture of small groups, how you can use the Seelos theorems. The best part of Seelos theorems is, well, for Seelos theorems, you are able to find really the existence, although we don't really guarantee anything about the structure, but the existence of some order subgroup of a group can be guaranteed. And we can even count how many this kind of group you have, okay? And then based on this fact, you can try to do a classification of small orders of, of groups of small order, okay? And among this kind of thing, I think maybe the hardest part is, well, how you can do this group action. It seems that we always change our object when we try to do the group action. We try to use some group to acting on the coset of a group, or try to acting on the orbit of the group, or a set, or try to acting on some group itself, or some subgroup, okay? So it seems that we have a lot of options. However, if you try to make a summary, you will find that, okay, if you try to run the group action argument, the only cases are just the cases I list above, okay? No more than that. So it's still finitely many options you will try to find about the group action if you would like to use the group action, okay? So in order to find the best way to use a group action, my suggestion would be, well, if you insist on group action, maybe you can try to do the triangle. This sounds very stupid, but it's the best way in order to do that. And then after you do enough problems about the group action, probably you will have a sense about, well, in which situation I can use this kind of group action, in which situation I can use the other one. Okay? So this are basically everything we have learned in this semester. Again, we don't learn a lot of things. Okay? This kind of thing, it sounds kind of very hard, very fancy, but whatever it is, whatever they are just a language, nothing more than a language. Okay? For instance, we've learned the term so-called the transitive. An action is transitive, or an action is faithful. Okay? But you can see that the transitive or faithful are nothing but just some properties about the homomorphism. Okay? So, well, it's nothing more than that, which sounds very easy if you try to go back to the original definition, but to learn this kind of terms, to know how to use this kind of terms is very important. Okay? Because otherwise, well, this is actually why whenever you try to read a math paper, you always find is well, you may understand every single terms. You may understand the meaning of every single terms, but you can never understand, well, the whole thing, the whole sentence, even the whole sentence. It's just because he trying to make it another kind of language that you have to know what does he mean by saying this kind of terms. Okay? And this seems very stupid. Why you cannot go back to the very beginning and state it in some easier way? Well, it's just because if you try to go everything back to the very beginning and use very beginning, very very easy terms to explain it, then everything will become super long. It's just like a very popular, very popular saying recently. You may be in level 1, okay? But those papers are already in level 5. So, which is why you are not able to understand it. If you want to understand it, well, then you have to know this kind of language in advance, okay? So this is something very important. Although currently in model math, in the model mathematics, it may be somehow go over too far away. Sometimes even you try to understand the motivation is something very hard, because the motivation may come from something very basic things. Okay, for instance, it may come from the number theory, problems in number theory. But then people find that that problem is over too hard. It may not be manageable for anybody. So they try to generalize these problems and make a particular problem somehow very generalized problems, and then try to study these generalized problems. And then they find that it's, of course, it's even harder than the original problem. So they try to study this generalized problem, then try to attack only one very little piece of this problem. Okay? And maybe they find that this very small piece of this problem is still very hard. Then they try to make this kind of small part things to some even more general thing. Okay, and then try to divide it into an even smaller piece. Try to study it. A lot of math paper is made this kind of argument and study some subproblems over subproblems. Okay, and then maybe little by little, eventually you can touch the original problems. But for some of the problems nowadays, or maybe I should say for most of the papers nowadays, it may be very hard if you try to get some result that is understandable for undergrad student, okay, especially in algebra or in some very theoretical analysis, okay. So this is why now you are trying to learn this language, okay. The reason why you try to learn this language is at least it gives you some hope. At least you can push little by little of a particular problem. Although nobody can guarantee that eventually you are able to solve the whole problem, but little by little, I think maybe eventually we will be able to solve a big problem in this way, okay? So if you want to solve a big problem, then to know this kind of language is very important. But as you can see, this kind of language is just the very basic one. It's just a little bit beyond your common sense. So which is why sometimes when you do not want to use this kind of knowledge, you are still able to solve the problems. For instance, like in your homework 4, most of you don't use any fancy terms or fancy tools that we provide in our class, and you still solve that problem. That's totally fine. I mean, that's also fine in your finals. But it may not be fine if you try to learn something more advanced, okay? So if you try to learn something in more advanced and you try to go back, everything go back to the very beginning, then it will be really time consuming, okay? If you are not familiar with this kind of language, then it will really make your life much harder when you try to do some real research. Okay, this is why we try to make everything, pack everything into some fancy word. Okay, it's not necessary. Well, at least at this stage, it may not be necessary, but you will benefit from it in the future. Okay. So this is basically what we have learned, and the philosophy or the logic or the structure about what we learned in this semester. Okay, and before we move on, any question? Any question about what we've learned in this semester?
Yes. Mm-hmm. Could you please explain again, what do you mean by like try different group action? Because I'm afraid I didn't catch you.
Yes, well, you try to use different group action is when you're trying to do something about, for instance, computing the order of something or try to find the order of group of something, then there are only finite cases that you can do if you try to run the group action. You can see that when we try to do the proof. Either you try to use the whole group or you try to use some subgroup, some normal subgroup or whatever P subgroup to acting on either this group itself or some subgroup or something like the coset of a subgroup or something like the conjugate classes of the subgroup. Okay? You only have this kind of finite many options. So when you try to run the group action, because you think that maybe the group action can tell you more information, maybe not in this final, but in the future, then you will not have a lot of things you need to try. Okay, only finite many. You can try to make a summary by yourself, but based on our course, well, we only need you to use some group or some subgroup to acting on some coset, some conjugate classes, some group. Okay, so that's all you need. So you can do that by trying each cases. Well, at most there are only like 8 cases or maybe 6 cases. So you can try one by one and see whether you can get some more information or not. Okay. Well, I think for this exam, you don't need to worry too much about it, because if I ask you to use some group action, either it is something we already seen, something very similar in our class, or I may give you some hint, okay, so that you know what kind of group action you should use. Okay, but after all, there are only finite cases. There are only finitely many cases for the group action. You do not have a lot of things you need to do to try the group action, because most of them you are not really able to use a group acting on. Okay?
Yeah, got it. Thank you.
Any other question? Any question about our final, about this course, or anything? Any question? Okay, if there is more question, then, well, let me try to tell you something just for relax, okay? Because I know this week you must be very busy and have a lot of pressure. So let me just show you something, and you don't need to worry about whether it will be in the final exam or not. Of course, it will not. But I think this is somehow interesting because, to be honest, I don't know how to play it before Spring Festival, and I try to learn it, and I find that yes, it's kind of interesting, and you can really use some kind of group knowledge in order to play with it. Okay, so let me maybe tell you somehow about this knowledge about the magic cube. Okay, let me try. Again, I just learned it by watching some video on Bilibili and just like 1 hour. So I'm not expert in this. So I will try to explain how I understand about the way to play with it. Okay. So as I said, this magic cube, it has 8 vertices. So you can try to see all these kind of operations as something on S8. Okay, you can see these operations as a subgroup of S8, or maybe the whole S8. I don't know. I didn't prove it. If you are able to prove it, then that's good. And basically, the operations you can do is you can rotate this side, or the right-hand side, or the left-hand side, or the top, or the bottom, either clockwise or counterclockwise. Okay. So there are a lot of basic options for you to do, and your point is you try to use this kind of operations to recover this magic cube. Okay, and in order to do that, I think I shouldn't mix this magic cube at the very beginning. I will just tell you. There is a very, very important operations we are going to use for this recovering of this magic cube. Okay, let's call this operation sigma. And these operations, it can be write as you rotate the right-hand side clockwise, and then you rotate this top side clockwise. Right, the right-hand side, let's say clockwise is R, and counterclockwise R inverse. Okay, and this is upper for the upper side clockwise, and then you do this right-hand side counterclockwise, and then do the upper side counterclockwise. Okay, this operation, let's call it a sigma. And at least one good thing is we know it is an element of S8. So this sigma must have a finite order. Okay, if we try to learn the sigma, then the sigma must have finite order. So which means we can play with it again, and maybe again, and again, and again, and again, and we got it back. Okay, how many times we play with? I think it's the order should be somehow, should be 6 or 8, whatever. It has a finite order. So you don't really need to worry about, sometimes you are not able to make it back make the inverse of this operation, because the reverse of this operation is somehow very complicated. But you can, well, if you forgot how to reverse it, you can always play it again, right? Because everything in SH has an order. And well, what else we can say about this operation? If you try to look at this operation, what you can find is, for this operation, if we try to play with it, then what happens is this 2 cube doesn't change at all. Okay, this 2 cube that face to you doesn't change at all. And on the bottom, this 3 doesn't change at all. Okay, whenever you play with it, this 3 doesn't change. This, and this. These 5 cubes are a fixed point under this operation. Okay, sigma, well, let's say 1, sigma this cube, sigma A1 equals to A1, etc. Okay, we know that at least there are 5 blocks that doesn't change at all. Moreover, what we can see is these 2 guys interchange with each other. You can see now here it becomes blue, right? This cube is blue, but originally the blue should be here. The blue should on the top. Okay, so which means you just bring this here. Okay, so which means this operation will interchange these 2 guys, these 2 cubes. It will interchange these 2 cubes. It will keep these 5 cubes, does not change. It will interchange these 2 cubes, and it will somehow rotate these 2 cubes as well. You see, these 2 cubes, they somehow exchange and rotate. And you can do even more. And you'll find that everything else, they just change, but these 2, they just try to rotate and exchange all the time under this operation. Okay, these 2 guys, eventually it goes back. We can do it again. You remember this is red, blue, and yellow. This one is red, green, and yellow. So if you do it again, you find that this is red, green, yellow. This is red, well, red, blue, yellow. Okay, so these 2 guys interchange, and these 5 cubes, they doesn't change. Okay, so this is a very interesting property, which is something we are able to use it at the first stage of recovering a magic cube. Okay, so it is a very basic operation. It is also a very important operation. So let me try to, well, let me try to make this magic cube somehow chaotic randomly. And then let me try to show you why this operation can help us to somehow recover it in the first stage. Okay, let me, well, for instance, mix it well. Okay, I think now is the well mixed, okay, as a magic cube. Then, if you have this kind of well mixed magic cube, the first thing you try to do is you would like to try to make this, for instance, 4 out of 8 4 cubes in the right position. Okay, how is that? Well, maybe we should start from something very beginning. Okay, let's try not to make this 4 to be the, well, to be the right position, but let's just try to make this 2. Okay, let's try to make, for instance, this 2 or maybe some other 2 to be on the right position. Right position, I mean, well, for instance, this 2, it seems that they have the same color, but if you look at the top of these 2, these 2 are not in the right position. Well, the one that behind, well, that next to this cube should be this one, right? It should contain this blue on the top. So this cube should go here instead of this cube. Okay, So let's try to make it closer to this cube. For instance, let's try to make it here, closer to this one. And then what we can do in order to make these two guys together, try to make these two guys together is, well, how about we try to use our operation so that these two guys will interchange, but this cube will not, right? This will be fixed. If we try to run our operation in this direction, then this two cube will try to interchange, but this one will not. This one will not. Okay? So let's try to do it. Let's try to run it this way. Right? Well, clockwise, clockwise, counterclockwise, counterclockwise. Now you see we have two cubes that forms an edge such that these two cubes are in the correct position, right? Blue, blue, and yellow, yellow. Okay, so these two cubes are in the right position. Okay, that's great. Now the next problem is we want to, for instance, we already think, okay, we're trying to make this blue one to be our base, okay, to be our base, because we try to make everything to be agree with this blue one, okay? So which means if we would like to make this whole 4 to be in the right position, then we want to move 2 blue on the top so that everything will be in the right position, okay? So let's try to find, okay, there is 1 blue here. Let's see whether, okay, we are lucky, then we have 3. We have 3 blue blocks that are in the right position. We are only missing one of the blue blocks, which is here, okay? Now, how to make this block here? Again, we can try to run our operation so that it can keep these 3 blocks, okay? It can keep these 3 cubes, and which means it can interchange these 2, rotate and interchange these 2, but keep this. So we can try. Clockwise, clockwise, counterclockwise, counterclockwise. Now you see, we have half of the magic cube is in the right position. Okay, these 4 are already in the right position. This is stage 1. Okay, this is so-called well, we can say it is stage 1. As long as you are able to recover the magic cube for these 4 cubes, for these four blocks, then you are finishing the first step. Okay, I think it's clear. If you don't understand it, that's fine, but this is just some idea about how to use a group action to understand this recovering of a magic cube. Okay, and then on the next stage, which is stage 2, what you're trying to do is, you trying to, since here it is blue, and well, next to blue, or the neighbor of blue, are, this is orange, this is white, this is red, this is yellow, okay? So which means, on the other side of this blue, is supposed to be green, right? Because green are not on this side, or this side, or this side. So now stage 2 is you try to put on this side to be everything to be green, okay? And you try to put the green in the right position. Now, what you're trying to do is you will still use sigma on the second stage. However, what you're trying to use is not really sigma, but sigma to the power 4, okay? And I'll not show you, well, what's a sigma to the power 4 will acting on it, well, how it really looks like, because that will make everything confused. But the property of sigma to the power 4 is if you run the sigma to the power 4 3 times. If you run it 3 times, what happens is, well, the right-hand side, you try to take this magic cube in this way, then the right-hand side will go back to this blue are in the right position. And meanwhile, if you try to do this sigma to the power 4 one times, what happens is this will be something chaotic. This will be something random. But what happens is it will change these two sides. It will change this block. If you try to hold the magic cube in this way, it will change these two blocks. Okay? So which means as long as you have one green here, and one green here, and one green here, and the other green is on this side of this magic cube, then you can try to play sigma to the power 4 on this magic cube by first make this green here, second make this green here, third make this green here. Then what happens is eventually you got the right hand side to go back to this kind of pattern, and on the left hand side you get everything to be green, which means the green are in the right position somehow. Okay, but unfortunately we're not really lucky in this times. So because there are two green here, two green here. Okay, so what I'm going to do is I'll try to run it 3 times of sigma to the power 4 and try to make it something we want. Try to make it like you have one green here, you have one green here, you have one green here. Okay, so that's try to do it. Hold it in this way and try to play sigma 4 times. Then you can interchange these two guys. 1, 2, 3, 4. Okay, so you somehow interchange these two guys. Well, not very good. And then the next thing we may try to do is maybe we try to do it here, because eventually we have to do 3 times. So let's try whatever. Let's try this one. Okay, so maybe this is not the best way to do it. Well, let's do it again. I'll see. Okay, so you can see that at least the blue one go back. And luckily, well, we have one green one here, one green one here, and one green one here. Okay, so we can run this sigma to the power 4 3 times again, and then all the green one will go to the top or go to the left. Okay, let's try to do it so that these two can interchange. Okay, this is the first thing. 2, 3, 4. Okay, now you see we have 2 green one here, and we have another one we want to move it here. 1, 2, 3, 4. Okay, the second one and the last one. 2, 3, and 4. Okay, now you see every green one at the top and every blue one on the bottom. Okay, so now we finish the stage 2. Okay, for stage 2 we have everything here in the correct position, and at least the top one you just need to interchange something. Now we can go to stage 3. Okay, the stage 3 is just something you want to move this kind of this 4 green one to the right position. For instance, this is not in the right position. You should interchange with this one, right? And then after that, I think everything is just in the right position. Okay. So for this thing, what you have to do is, you may have one side that is, everything is just seems to be in the right position. For instance, on this side, if you try to play with it, you'll find that, okay, the blue one are in the right position, and the orange one is also in the right position, and the green one are in the right position. Now, if we try to make it back, we'll make it somehow what we want. What we try to do is, this is a magic way. The last step, I don't really understand it. You can try to understand it by the group theory. But the last step is you try to use sigma to the power 3. Okay? And then sigma to the power 3, then you times something like you rotate the bottom. You hold this magic cube in this way, okay? Right hand side is this this side, and the top is a blue one, which is you already got the right position, and the bottom one is something you want to change, okay? It's a sigma cube times you rotate 90 degrees for the bottom, counterclockwise. So it's bottom inverse, and then sigma cube, then counterclockwise, then sigma cube, and then you take 2 times of the bottom counterclockwise, and then sigma cube. Okay, it seems very complicated, but it's something that's doable. Okay, let's try to do it. So 3 times of sigma. 1, 2, and 3. Okay, then you can see that on the bottom you have a block here. You have a uneven block here. Then you try to move it counterclockwise 90 degrees. Then 1, 2, 3. Okay, this block move it doesn't change. Then you try to interchange it 180 degrees. Then 1, 2, and 3. Am I right? It seems that I don't do it correctly. I don't do it correctly.
I think like the first rotation should be like clockwise.
Is that clockwise?
I mean,
I think it's still counterclockwise. Well, let me see. Okay. At least it's not so bad. We go back to this. Let me try. As you see, I'm not an expert. So yeah, I always make mistake. So again, we move everything to be the same, and to be on the right hand side, this is the top. Let me see. 1, 2, 3. And clockwise. I think it's counterclockwise. Yeah, I think it's counterclockwise. This is a counterclockwise because you try to see it this way. Okay. 1, 2, and 3. 1, 1, 1, 2, and 3. Okay, great. Yeah, then we go back. It seems that I made some mistake. Then you can see that every cube are in the right position. Okay, so there are 3 stages. Maybe my explanation is not as good as someone else, but the idea here, you can see that the idea here is you try to use then the operations, and you try to study these properties of the operations. You try to see, okay, what are the fixed point of these operations and how we can use them. Okay, what does this operation change and what does it keep? Okay. Anyway, so yeah, this is just well, one examples. If you want, I can play more, but it's already 1 o'clock. So yeah, if you are not really interested in Magic Cube, and we can just postpone it, and I will have the office hour, let you ask any questions. Okay. So feel free to go if you do not have any questions, and otherwise you can just stay here. I'll be here until 3 o'clock. Okay. And well, thank you for this semester, and well, I hope you have good luck for your final this evening. It's slightly harder than the midterm, but I think it's still manageable for you guys. Okay.